In today's episode, we are going to get to the world of quantum theory. Before there, let's just talk about, the history of how we got to where we are today. You don't need to copy this stuff down, it's not necessary. But, for the longest time, we've been trying to organize things and trying to make sense of this world that we live in. There are a lot of stories that explain how the world works, and, there's a lot of explanations explaining, how matter is created. And even though these things may be dated by today's standards, they got us thinking about looking to see if there's any patterns out there. In fact, one of the first few people that actually made it into the physics textbooks is good old Galileo Galilei. Right? He was one who discovered that there is such thing as not only uniform motion but also uniform acceleration as well. Rene Descartes was able to, mathematically correlate things together, and create the world of calculus to form things together. And again, I don't want to bore you with all the stories of all these other scientists, all right? But you've probably heard of their names before in earlier units, all right? And this is still classified as classical physics, at least up to this point over here, all right? And then afterwards, we move on to just the beginning of modern physics, and that all starts once we understood that, elements are used to make compounds. Now, this becomes a very fuzzy and gray area. What is classified as modern physics and what is classified as classical physics? In many textbooks, they just use the number of 1900 as a threshold. And, I guess I'll go with that as well. Right? So pretty much everything in the 20th century and beyond is generally what we classify as modern physics. Right, and that's what we'll be focusing on over the next few days. All these crazy things that you may have heard of here and there. In fact, one of them that we want to talk about is this photoelectric effect, where it was first discovered by Philip Leonard, but funny enough, it was Einstein that got the Nobel Prize for it because he was able to explain the true patterns behind it and the equations that underlay it as well. All right, so yeah, that's our focus over the next while. To quickly get us up to speed, I have this really cool video to share with you. You can follow along with me in your course pack. Of course, due to any potential threats of copyright infringement, I'm not going to play this video for you, so please watch the video on your own, fill in the course pack, and here are the corresponding answer keys to the course pack once you're done with it. Of course, beyond here, what's new in the world of physics? I think this clip should be sufficient to tell you the answer.
So, what's new in the world of physics?
Nothing.
And that explains it. All right, a bit more from grade 9 science review. You might remember seeing this lovely table before, expressing the fact that, what we can see is a very small slither of this entire thing called the electromagnetic spectrum, right? And things I want to point out from here is that, for one thing, when you take a look at red light, yes, it is at a lower frequency, but it also has a longer wavelength. And if you compare it to the other end with ultraviolet light, it has a higher frequency and a shorter wavelength. That's one property. Another thing that this diagram fails to explain is the amount of effort required to create this higher energy. I mean, if you guys have ever played with these types of ropes before, these battle ropes, you might notice that it takes a lot of effort in creating these waves. Now, if you move it very quickly, the waves start to compress. But if you move it very slowly, the waves spread further out. Right? And that's another thing I want to emphasize as well. At lower light frequencies or longer wavelengths, it requires less energy to create these photons of light, and they also carry less energy with them as they pass through space. And on the flip side, with regards to UV light, it takes more energy to create a photon of that light, and as it flies through space, it contains more energy per packet. In fact, in this regime of the entire electromagnetic spectrum, usually ultraviolet and beyond, this is also known as ionizing radiation. In other words, the energy is so high that it is possible to cause electrons to be ejected off surfaces, and more on that later. Right. Meanwhile, stuff down here, including your good old microwave in your kitchen, it's classified as non-ionizing radiation, so technically it's safe to be radiated with microwaves in your kitchen. Not that I really trust that, but at least with the physics, it's technically true. All right. Still wouldn't stick my hand in a microwave. Anyways, let's go through the details of Philip Leonard and what he noticed. All right, so he created this crazy-looking contraption. I just want to share with you what this contraption is about. All right, so yes, there's the positive end and the negative end, And what he did was that he gradually changed the type of metal that he used on one end of this system over here. All right, and he would let light bombard onto that piece of metal. And depending upon which element it is, either it let go of the electron very easily and let it travel through, or it was frugal and it did not let it go through, and it would just, bounce right back to um, the original source. In fact, it doesn't bounce back; it just stays there and stays put. All right, and yeah, he would do things like, for example, give a little bit of nudge to the electrons. For example, if you hook it up like this, then you have an abundance full of electrons over here, and you'll have a slightly positive charge over here. And since electrons love positive charges, they will naturally want to flow over here. So yes, you could have a situation where there's no light at all, and if the voltage is high enough, the electrons will just simply jump through the gap and eventually make it to the other side. All right, but well, at a very incredibly high voltage. But here's the thing, that's kind of pointless in doing. But the cool thing is that if you introduce light into it, you may cause the electrons to naturally want to jump across. In other words, on the far end, if you replace that battery with, I don't know, let's say a light bulb instead, then you're able to convert why a light bulb? Let's say motor. Yeah, that makes more sense. Here's a motor. Okay, so you'd rather convert the light into moving current, and with moving currents, now you can do something else like make a motor spin. In other words, convert this into a solar panel. All right, and that's a cool thing that Philip Leonard noticed. But there's a lot more to just that basic story over there because there's a lot of catches. So let's go through all the catches. All right, first off, the current is directly proportional to the light intensity. In other words, the brighter the light, then the more current that will flow. But that's it. It will not affect your voltage. It will just increase your current. Number two, this stuff only works if the color of light, which corresponds to its frequency, is at a certain threshold. And if you recall, with red light has a, let me redraw this again. With red light has a longer wavelength, and then as you go to violet light has a shorter wavelength. All right. With red light, again, there's low energy here associated with each packet, and with violet light, there's a high quantity of energy per packet. So if the light frequency is too low, then there won't be enough energy to eject the electrons to allow them to travel through. All right, so you need to have a light of a certain frequency in order for current to flow. That's what the second statement's about. All right, and the threshold is known as F naught, by the way. All right, and that F naught is based upon what you chose as your metal that you placed over here on the plate. Potential difference, what is this about? Oh yeah, you can play around with the circuit, that's all. Okay, you can play around the circuit and eventually you can find out this stopping voltage, which is in a sense kind of like a weaker calculation in figuring out how to make things work. In fact, yeah, let's go through an animation right now so that we can better appreciate what's going on. And yes, with regards to the stopping voltage, as you can read over here, once you end up creating that stopping voltage, then no matter how hard you try, you're not going to cause the electrons to want to jitter free. And there are two versions of this PhET simulation. I have the original one which is written in Macromedia Flash, and then there's a more modern one available online. I'll use this one for now, but you can try out the modern one when you're at home. So Control A, yeah, just to open up this Flash file. There you go. Okay, so yeah, let's use this picture over here to describe all these things over here. The current is proportionate to the light intensity. So for one thing, in order for this experiment to work, I need to go off and hit it with some UV light. Why UV light? Because there's more energy per packet. In fact, let me just show you this, okay? The UV light, because it's UV light, that's why the electrons are able to eject. If I bring it over to infrared radiation, there's not enough energy per packet of photons to want it to eject. All right, so that's why this happens the way it does. Okay, so let me bring it back to UV light. And you can see that as I bring it more and more into deep UV, more electrons are ejected. In fact, there's more energy associated with the electrons that are ejected as well. All right, and if we want to adjust the quantity of electrons that are ejected, we have to change the intensity of the light. Here it is at 100% intensity. You can see there's a lot of them going through. If I bring it down to about 50%, about 50% of them pass through. And as I lower the intensity, less of them pass through. Okay, they all have lots of energy in them because I'm using UV light, but less of them pass through. All right, so current is directly proportionate to light intensity. The greater the light intensity, the more electrons that will fly through. All right. Meanwhile, the frequency of the light will tell you how much energy there is per packet. And you can see that as I increase the wavelength or lower the corresponding frequency, there's less energy per packet as they exit through. Okay, and this is at a fairly bright intensity. That's why there's a lot of electrons passing through. But if I decrease the brightness or the intensity of the light, then just less of them will pass through as time goes by. And that's it. Okay, the F naught. Oh yeah, choice selection of your material. Now sodium tends to allow electrons to be ejected quite freely and readily. All right, so let me just give you more of them just so you can see that that happens, and I'll just bring it to a low enough value to show you that, yeah, that happens with sodium, right? Meanwhile, is there aluminum? No, there isn't, but copper is one which loves to hold onto its electrons. So if I switch over to copper, you'll see that, hey, well, the electrons aren't going anymore because copper loves their electrons. So, I can increase the intensity of the light and nothing will happen. In order for the electrons to eject, I need to bombard it with even deeper UV light or UV light of a even shorter wavelength where there's more energy per packet. And then the electrons will move. Okay, so this is a less sensitive solar panel, I suppose. I'll switch over back to sodium again because that one, you can see that sodium wants to get rid of the electron rather quickly. And there you go. There's the proof of that, I guess. What is this? The reverse voltage. Oh, yeah. So let's go off and reverse this through. For one thing, let me just reduce the intensity of the light just so there aren't that many electrons going through. And yeah, you'll notice that if I forward bias this to positive 8 volts, that means that this plate here is positive and this plate here is negative. Of course, yeah, sure, it's going to allow this thing to happen a lot more rapidly, right? Because what you're doing is you're creating a strong negative plate over here because there's a bunch of electrons, and electrons hate a lot of electrons, and they'll quickly want to move across. So if we end up flipping the battery onto the other side, well, hey, take a look what happens now. This plate is slightly positive, and you can see that not all the electrons make it through. Many of them love the positive plate so much more, so they flip to this direction here. All right, so let's go and figure out our stopping voltage. So we're going to reverse bias this to a high enough value where they're not traveling through anymore. All right. In fact, I can try to bring the light as bright as possible, and none of them will make it through. And that's the interesting thing about the stopping voltage, right? So once you reach this critical threshold of the stopping voltage, no matter how hard you try, the electrons are not going to flow through. You're not going to have any current flowing through the circuit. Okay, and yeah, there's a bunch of graphs that you can activate and play through, and I would strongly encourage for you to play with all these and manipulate the settings, because once you manipulate them, you'll end up creating these real-time graphs, right, showing you what's going on as you continuously change all these variables. Okay, but I'm going to summarize for you all these outcomes over here with the graphs that we have down here. Okay, so we talked about the fact that if if you don't reach that certain color of light, that's more or less in the UV spectrum over here, and over here will be in the red end spectrum. Yeah, the frequency is not high enough. Unfortunately, no electrons will be ejected. You need to reach that critical frequency of light before electrons will travel through. All right, so I think that's the first figure's emphasis. And the second one here is talking about that stopping voltage. You remember I reverse biased it, and that's why it's negative, because the current direction is going backwards, also known as reverse biasing. That, yeah, once I reach that threshold, no matter how bright the light is, unfortunately no electrons will want to move. Okay, so I hope that this explains it, and that's why I encourage for you to try out these simulations on your own. It doesn't matter if you do this version over here or the one that I'll show you at the end, right, which is the online edition one. Okay, armed with that knowledge, let's talk about these ideas as well. Okay, remember how I mentioned that depending upon the metal plate that you choose, either it will love the electrons and it will hold on to it aggressively. That's why I was trying to look for aluminum, but it didn't exist in the simulation. But hey, whatever. Copper was even better, right? Copper, it didn't want to let go of the electrons. All right. Meanwhile, I knew that, for example, sodium, it has a lower work function. All right. And again, the work function by definition is the minimum energy needed to remove the electron bond from that surface. All right. So some of them let go of the electrons easily, others hold on to them quite intensely. All right. And again, this photoelectric effect, which Albert Einstein actually got a Nobel Prize for, he was the one who was able to see all the math and the proofs behind them all. All right. So what are we going to go through? Okay, first off, we'll just go through some random metals, and this is what you'll notice each and every single time when you bombard, the surface with intensity of light. Okay, so with material A, once you reach that critical threshold, that minimum frequency to allow the electrons to eject, then you'll notice that there are more electrons that are being emitted. All right. In fact, they'll have more energy per electron as as you increase the frequency of light. Okay, so there's more energy per photon of light. Okay, so that's material A. Material A, in comparison with material B, requires a lower frequency, so it requires a lower work function. And material B requires a higher frequency, and it requires a greater work function. In fact, if we were to imagine another material over here, that's material C, again, it needs a higher frequency. But here's the interesting thing about these diagrams over here. I think it's animated over here. Take a look at these three lines. You'll notice that they're all parallel. They all share the same exact slope. And that interesting thing about that slope over there is that you can create that slope as a constant. And that constant is named in honor of Max Planck, and it's known as the Planck constant. All right, so the slope, do I have it animated over here? Yeah, the slope is Planck's constant, which is this number over here. I know I'm going a little bit ahead of myself, but here's another thing about this, all right? Since we know that this is Max Planck's constant, and that constant there is the same for this slope, which is the same as the slope over here, which is the same as the slope over here, if we extrapolate all of these over to the y-axis, if you want to call this the y-axis, they all have a different y-intercept. Remember how I said that material A required a lower frequency in order for it to eject? Then it'll have a lower work function. So effectively, this y-axis over here is the work function. Okay, so the reason why I'm sharing you with that is that eventually we want to go and reuse more grade 9 memories of y equals mx plus b, because we just talked about the whole b concept over here. And we know that m is going to be replaced with x. And what is x going to be? Well, x corresponds to its frequency. All right, so we're going to derive that equation out. First off, here's the formula about how much energy there is per electron once it's ejected. So again, at higher frequencies, there's more energy per electron. I'm using the example of material A. All right, so as the frequency increases, there's more energy per electron that's been ejected. In other words, the voltage will increase if it's flowing through a circuit. All right, and then we come up with this formula over here, which by definition is our work function. Okay, so our work function is based upon the frequency multiplied by the slope. Effectively, we're looking for the y-intercept over here. Okay, so this is the y-intercept. Well, then if we want to find out in total how much kinetic energy there is in that packet of photons, or the electron that's been ejected, then what we need to do is that we need to multiply the slope by our x value and subtract it by our y-intercept. So I hope you can appreciate how that formula here is derived from this. Once again, as a reminder, when you increase the brightness, all you're doing is increasing the amount of current. That's it. All right. You will not be able to increase the voltage. Voltage remains the same. That's another thing to point out. I think armed with that knowledge, we can move on to a sample calculation. Calculate the minimum photon energy in joules and the corresponding frequency and color of light that's needed to emit electrons from a plate of aluminum. First off, we need to rewind back and take a look at the work function of aluminum. Right, we need that constant there, so you need to look that up on a lookup table, or it's given to you like so. All right, now this work function is measured in electron volts, and we need to measure it in joules. And if you recall earlier, 1.602 times 10 to the negative 19 joules is equal to 1 electron volt. All right, so if we want to convert to joules, then we need to go off and multiply it by 1.602 times 10 to the negative 19 joules per electron volt as our conversion ratio. All right, so now we have our work measured in joules. Now remember, the work function is the minimum energy that's needed to eject that electron off the surface. All right. So it effectively is the y-intercept when you go through the calculations. So let's go off and figure out what that frequency would be. So if we know that W work function is equal to Planck's constant times the threshold frequency, then we can rearrange it for the frequency that's required. All right, so we'll divide the work measured in joules by Planck's constant of 6.63 times 10 to the negative 34, and that'll tell us the minimum frequency of light, or the color of light. However, often when we talk about light and color, we don't measure it in frequency. Instead, we measure it in wavelengths. So that's when you have to take out this equation from grade 11. V equals F lambda. Of course, we're talking about light here. So the speed of light is at 3 times 10 to the 8 meters per second. In other words, we can replace V with the letter C. All right, so taking this formula and isolating for lambda, we have lambda is equal to C divided by F, and we get this answer over here. Now, I know that not everyone's familiar with wavelengths and colors, so that's why there's a lookup table over here. All right, so in general, red light is somewhere around 600 nanometers, green in the mid 500s, and blue is in the mid 400s. I think those are good reference values. All right, and everything's all subjective with regards to color because everyone has their own definition of what red is. So these are not international standards. These are just reference values. So that's why we have approximate over here. All right, but definitely anything that's above 700 nanometers, those are very long wavelengths. That's in the infrared spectrum. Same as anything that's much lower than 400 nanometers, that will be in the ultraviolet spectrum. So what does that make this color over here? Well, that must be a light that we cannot see, and that's the reality. When you do this experiment over here, you'll be shining something at the surface where the human eye can't see it, but you'll notice that you end up having electrons emitted. But this is very dangerous light. All right. As you may know, with UV light, if you shine it on your skin, you're not going to see anything because your eyes can't pick up on it. But over time, you're going to end up burning your skin because there's so much energy in the packet of UV light. Okay, so yeah, this is just a cool little story just to share with you on the side. Maybe some of you guys will appreciate this. With regards to the world of photosynthesis, photosynthesis works really well under these wavelengths. You'll see that there's a wavelength that's somewhere in the 400s, so somewhere in the blue end of the spectrum that it receives very well, and then somewhere in the 650 nanometer spectrum where it's going to absorb very well as well. I have a YouTube video about it. If you ever go to Costco, every now and then they sell these lamps where if you take a look on the underside of the lamps, it's bombarded with nothing more than blue LEDs and red LEDs. All right, and the reason for that is because that's what encourages photosynthesis to occur, not green. You can see that green doesn't help it whatsoever. In fact, I hope you can appreciate, the laws of light reflection here now. Why are the leaves of plants green? Hope you could figure out that clue on your own. All right. Yeah, there's some really cool pictures with regards to this. If you're into ultraviolet photography, it is actually quite beautiful. Now, really, we can't see UV light, so what they did was they took pictures using UV light, pictures of environments in the UV spectrum, and then they colorized it just to make it look a lot more interesting. All right, so it's a pretty cool type of photography. One last demo I'd love to share with you. It just doesn't work well in this medium, so who knows? Maybe I'll make a YouTube video on this cool thing over here. All right. Aside from that, again, I would encourage for you to try out the online edition of this. Let me try opening up here just so you can see what it looks like. And it's very similar to what I had, right? So go ahead and try it, work through this, mess around with all the values over here, run the animation, and, I hope you have a better appreciation of the photoelectric effect with this. Aside from that, go through the simulation, answer the questions and homework, and I'll catch you in the next episode. Bye now.